So, two questions, Tobias. Firstly, concurrency. Do you tackle concurrent algorithms? And secondly, much more on the pedagogic side, do you examine the course at all?
Right. No, I'm afraid concurrency is not in the course. And I think it's one of those things that if you added it, it would complicate matters considerably, because in a functional world, it's not so clear. Then you go to multi-threading. And so it's all, I think it's concurrency is more easily tackled in an imperative context. That's, or you can say, well, in a functional context, you don't even need to tackle it because everything is by nature concurrently. But that's, of course, only a half truth.
Yeah. And do you have to examine the course?
Yes. And that works actually very well. So we had to examine it on paper in the past because those are the rules. But then with the pandemic, the rules were relaxed and we could examine the course online. And so actually the exam, we've conducted it twice online, and the students like it because they always felt that programming on a, or many of them feel that programming on a piece of paper is somehow an odd thing to do. And so we are quite happy with that mode of examining it. So the students, throughout the course, they get one homework sheet per week, and then they submit their Isabel theories, and it's graded automatically. So that's a big, of course, simplification for us, a big facilitates matters. And then the students are used to this grading process by submitting it to an online system, and then we use the same thing in the exam. And the numbers are small enough. We're talking about, like, in the final exam, like 40 people, that plagiarism is not a problem. People who, it's an elective course, so people who don't like it drop out anyway. I mean, we have very, for the homework, typically once every 2 years we have a problem that somebody copied homework. But yeah, it's not a major problem.
Okay, thank you, Cliff and Tobias. So we have a question from Matthias.
Yeah, hi. I would be interested in hearing about what you think are the big challenges for the students. Is it like thinking the right thing and then the difficulty to get it down in the form that the theory improver understands it and actually finish the proof, or is it understanding the really details of the algorithm or the data structure at hand?
No, sorry. No, the understanding the algorithms and the data structure at hand is typically not a problem for them. They even know some of them already. So they spend most of their time on, it's difficult to quantify this. I think there are 3 sources of difficulties. One is obviously the proof assistant, learning about its idiosyncrasies, just understanding the principles, all of that. A second difficulty is really writing down a coherent proof and getting confused about how to prove something with an existential quantifier in it, or how to deduce something from an existential quantifier. That kind of thing, it takes some time to get used to. And third, it's actually the difficulty of writing code that's simple. So in their homework, they have to write their own code, and then they typically come up with code that's too complicated, and then the proofs become insurmountable to them. And so we always tell them, if they run into problems, the first thing you should do, you should examine whether there's something too complicated. You've got too many case distinctions, whatever. And I think that's actually a major learning outcome of the course, is that you are forced to simplify your code because you have to prove it. And those are the three difficulties. And I cannot quantify how much is what, but certainly the contents is not, I mean, the abstract contents is not it's not the key difficulty. Yeah.
Okay, thank you, Matthias. We now have a question from Claudio.
Okay, first of all, thank you for the great keynote. It was really insightful, and it was nice to see all this history of success of FM techniques. Now, since I've seen that there are many young researchers attending the workshop, I found that the part about open research problem was fascinating. My question would be, I mean, do you have a website where you are collecting open research problems? How kind of, if there is some, how can you distinguish by problems which are easier and FM techniques can be, let's say, easily applied? It's just that someone didn't spend time of this, or like more challenging one?
No, we don't have a website on this. We considered, but never did get around to, I referred to this paper at ADVA last year, where we really give a detailed survey of verified algorithms. Yeah, we thought of turning that into a web page, and then you could update it with new verifications, but we never got around to that. And I certainly don't have any resources that would help young researchers to choose a suitable topic in this area. So yeah, that's all I can say about that. But maybe we'll do that web page after all, because now in the year that's passed since the publication of the paper, I've become aware of further verifications like this verification of Dijkstra's algorithm really at the C language level that should be incorporated in this survey. Yeah.
I have a follow-up question if there are no other one. It's related to the teaching part. And I would like to ask you whether kind of you can reflect a bit on something you did wrong during the course or during the pandemic, something that didn't go well or didn't go as you expected, and kind of some reflection on how, or I mean, if you have any insights to share with the community on how you would have improved that.
That's a bit awkward because I can't think of anything offhand, but that sounds terribly vain.
I know it's a bit a provocative question, like.
Yeah, it's a good question. I think what I would wish to do is I would wish to be able to cover more of the advanced material in more detail. Or detail is the wrong word. Let me say something that I'm really a bit unhappy about is these final algorithms that I'm teaching, the pairing heaps, the splay trees, and the skew heaps. And the amortized analysis of those, I don't really understand it myself, in the sense that I can do the math, but I do not understand the abstract reasoning behind it. Why does it work? And now I asked a colleague who's in algorithms, and in the end, his reply was, well, you just have to do the math and then you see that it works. So he didn't have a good explanation either, but I find that was a bit frustrating for me, that there were some advanced topics that I couldn't give the students a nice intuitive explanation of why the running time works out. But that's not quite what you were asking. So during the pandemic, I found I found it worked well, the online teaching, and the fact that it's programming oriented, I think helps. It's not so much concept oriented where you have difficult to grasp concepts, but it's mostly yeah, it's time consuming because working with systems is time consuming, but it's not something where you would say, oh, if you were in a classroom, you could convey these concepts much better than you can convey them online. Yeah.
Thank you.
Okay, thank you, Claudio. Maybe just a follow-up question on this last one. So if someone would like to start teaching from your book and repeat essentially what you are doing, is there any advice that you have that might avoid some problems that you encountered in the last 5 years? Or put it in a different way, if you were starting now, with all the experience that you acquired throughout these 5 years, would you do anything different from what you've done in 2017, for example?
One minor thing is that it's very important to have some kind of a feedback channel. What do we use? I think we use Zulip for the students to ask questions. So they get stuck in some proof and they get some error message that they don't understand. And then to be able to post that and get feedback from either other students or the tutor. I think that's an important point. But I think that also applies to programming courses. It's not unique to theorem proving or formal methods. Something I would, I think you should probably be familiar with the proof assistant yourself before you start teaching it, but I think that's a kind of an obvious thing. Familiar doesn't mean that you need to be an expert, but you should be reasonably familiar with it. Yeah.
Okay.
Otherwise, there's nothing that comes to mind now that I think we did wrong in the beginning, and I think we then corrected. No, I'm reasonably happy with the material as it is. Yeah.
Okay, thank you. So just to finish, one last question. We have Rune King who wrote in the chat window, and he asked if you have any plans about teaching formal mathematics using Isabelle.
No, I don't. And the reason is simply that I'm teaching computer scientists and the math courses are taught by the mathematicians. And so I think I would love to do more of this kind of teaching in a more mathematical area. For example, I've been toying with the idea of teaching the logic course based on a theorem prover, but haven't found the time yet to do it. There is some very encouraging experiments being done at, I think, Imperial College by Kevin Buzzard using the lean theorem prover. And of course, we'll also hear from Jeremy Avigard. What he did, I think, is a good vehicle. He said, I'm teaching a standard math course, but I'm also teaching the theorem prover, and optionally, the students can hand in their homework using the theorem prover, but it's not something that I will force on everybody. And I think that's the right way of approaching it if you're doing if you're teaching a mandatory course. But I'm not going, I'm just not a mathematician and I'm not teaching math courses. So that's the short answer. But I think we should see more of that kind of teaching where we try to integrate formal methods, or in particular theorem proving, into a standard curriculum by making it an optional component. I think that's a good, that's a nice idea.
Okay, well, thank you very much to Rune King for the question, and thanks again, Tobias. It was a wonderful talk.